Welcome to qnawire.
Because such little information is provided in this problem, there are multiple ways in which you can answer this question. There's only two pieces of information provided: the mass of calcium carbonate that was collected and the decay rate. The way that I'm going to show you is going to be focusing on the number of moles of carbon that are present in the calcium carbonate. So we'll start with the mass of calcium carbonate, convert the mass of calcium carbonate into moles calcium carbonate by dividing by the molar mass calcium carbonate. Then when we are in units of moles calcium carbonate, we can convert to moles of carbon, recognizing there's 1 mole carbon in 1 mole calcium carbonate. And we get 4.576 times 10 to the negative 2 moles of carbon. So, we can now calculate the rate of decay if we have this many moles of carbon in present day. Meaning, we have the regular natural abundance of carbon-14. To calculate the rate, then, at time 0, we need to know the rate constant. The rate constant can be calculated from the half-life of carbon-14. Half-life of carbon-14, 5,730 years, can be divided into the natural log of 2 in order to get our rate constant at 1.21 times 10 to the negative 4, 1 over years. Rate, then, is equal to the decay constant multiplied by the number of radioactive nuclides, or the number of carbon-14 nuclides. The decay constant that we calculate up here is in units of 1 over years, but ultimately we want a rate that has units of what are found in the problem of decays per minute. So we need to convert our years into minutes. 1 year is 365.25 days. The 0.25 comes from leap year. And there's, in 1 day, 24 hours. And then in 1 hour, 60 minutes. So this right here corresponds to K in units of 1 over minutes. We'll then take the moles of carbon that we have in our calcium carbonate. We'll recognize that all of these are not carbon-14, and we'll adjust for it in just a minute. We'll then convert, or we'll multiply the moles of total carbon to number of carbon atoms by multiplying by Avogadro's number. Then, recognizing all of these carbon atoms are not carbon-14, we'll use the current isotopic abundance of carbon-14 in nature, which is known to be 1 times 10 to the negative 12. This is the fraction of all carbon atoms that are carbon-14. So if we had this many moles of carbon, we would have this many radioactive nuclides of carbon-14 if we were in present day. This then will give us the rate that the charcoal would have had at time 0. We'll then compare the rate, assuming the maximum amount of carbon-14 at time 0 that we calculate here, to the rate that we currently get with the dried calcium carbonate. We carry out this calculation and we get 6.338 decays per minute. We can then use the first order integrated rate law to take the decays per minute at time t, for the sample, which was given to us, divided by what the rate would be if it had the actual current present day fraction of carbon-14 nuclides, essentially none has decayed, and set that equal to negative k multiplied by t, the time that needs to pass, and we get t equal to about one half-life, 5,650 years.